This video is on formal charge and how we use formal charge to ultimately decide on the best Lewis structure. So the definition of formal charge is basically it's the charge an atom would have if the electrons were always shared equally, or if all atoms had equal electronegativity values. It's kind of like a bookkeeping of valence electrons and keeping track of them when we have a Lewis structure. So how do we calculate this idea of something called formal charge? And it's a wordy discussion, but the underlying idea is fairly simple. So how we calculate formal charge is we take all the unshared electrons, so those would be like lone pairs, that are assigned to an atom, and we count those electrons as being assigned to that particular atom. And then for any bond, we take the bond and we split up the electrons and we give half to each atom in the bond. So this idea of formal charge revolves around calculating how many electrons are assigned to each atom. And so thus the big idea here is that formal charge can be calculated by taking an atom's valence electrons and subtracting from that how many are assigned with this counting measure that we just discussed. So the first thing we have to be able to do is calculate formal charge for each atom in a Lewis structure. So I'm going to change my color. So in this Cn minus structure, if I was going to calculate carbon's formal charge, so carbon's valence electrons are 4, and I'm going to subtract from that how many electrons are assigned to carbon in this particular structure. So it has 2 unshared electrons, which obviously get assigned to carbon, and then this is a triple bond. So there's 2 ways to think about this. A triple bond is 6 electrons, and so I would break that in half and say carbon gets 3 of them. Or I teach students to kind of physically, or at least in their mind, break that bond in half and then count, 1, 2, 3 electrons. So in this case, carbon has 2 that are only belonging to carbon and 3 from the bond, so that's 5. So in this case, carbon has a formal charge of -1. We'll do the same thing for nitrogen. Nitrogen has 5 valence electrons minus, in this case, nitrogen also has 5 assigned electrons, giving nitrogen a formal charge of 0. Sometimes you'll see me do the formal charges like in little boxes to identify that that's a formal charge. Also, one idea to think about is that the sum of the formal charges will equal the charge of the ion. Okay, so in this case I had a -1 and a 0, which when I add together I get -1, which does in fact equal the charge on this ion. If you have a neutral molecule, like in this second example with SO3, then my formal charges should add up to be 0 because the molecule's charge is 0. So you can always kind of check yourself that way. If they don't add up to be 0 and the molecule is neutral, then you have made a mistake somewhere. Okay, so if we're going to do the formal charges in SO3, so this left-handed oxygen, of course we take 6 valence for oxygen, and then we count 1, 2, 3, 4, 5, 6 are assigned plus 1 here, so that's 7. So this oxygen has a -1 formal charge. Notice this oxygen is going to be the same, 6 minus 1, 2, 3, 4, 5, 6, 7, so that's going to be a -1 charge. This oxygen is going to be 6 minus 1, 2, 3, 4, 5, and 6. So this oxygen has a formal charge of 0. And then sulfur also has 6 valence electrons. And in this case, sulfur's only got 1, 2, 3, and 4 assigned, giving sulfur a formal charge of +2. Again, based on what I just said, if you take a formal charge of 2, -1, and 0, they add to 0, which is the formal charge, which is the charge on this whole molecule, so I know I'm correct. Okay, so formal, that's like a fine discussion, and it's great to be able to calculate a formal charge, but what on earth are they used for? And what they are ultimately used for is choosing between Lewis structures when you can actually draw more than one correct Lewis structure for a molecule. So a kind of a famous example is carbon dioxide. And so if we draw carbon dioxide, we know carbon brings me 4 valence, each oxygen brings me 6 for a total of 16 electrons. Carbon's going to be in the center with my 6 electrons on each oxygen and my 4 on carbon. And so probably going to be a wise idea to create a double bond. And then there's another screaming set of electrons who are asking to be made into a double bond. And there we have carbon dioxide. Everybody has an octet, and there are 16 total electrons in my picture. However, there's actually a second way. So let me put my electrons back in. Bond. Okay. And then what if I form a double bond here? And then this might seem like it wouldn't be the the thing that sticks out to you the most, but what if we took this electron and moved it here? Okay, and then what if I took, which this is totally legal, these 2 electrons, made a triple bond. So in this case, everybody still has an octet. You can verify that, and there are actually 16 electrons, 2, 4, 6, 8, 10, 12, 14, 16. So both of these structures are technically correct following the rules of Lewis structures, but one of them is the dominant structure, and we base that on formal charges. So we'll talk about how we pick in just a minute, but let's go ahead and calculate formal charges first. And we do that for every atom in all the structures. So oxygen over here is going to be 6 minus 1, 2, 1, 2, 3, 4, 5, 6. So this guy's got a formal charge of 0. Carbon's going to be 4 minus 1, 2, 3, 4. So also a formal charge of 0. And the same 6 minus 6 with this right-handed oxygen. In the second picture, I have 6 valence for oxygen, minus 1, 2, 3, 4, 5, 6, 7. So it's a -1 formal charge. Carbon's going to be 4 minus 4. And then the right oxygen is going to be 6 minus 1, 2, 3, 4, 5. So that's a +1 or just 1. Again, in both these cases, all my formal charges add up to be 0, which is the correct rule because my molecule is neutral. Okay, so which structure is correct? And you might be able to guess, but there are 2 guidelines that will help us in that discussion. So the first one is that the dominant structure has formal charges closest to 0. Okay, so in this case, that's the only rule we need to pick the dominant structure, because I have one Lewis structure with all formal charges of 0, and then I have another Lewis structure that has -1 and a +1. So based solely on this first guideline, we can pick that this first CO2 picture is going to be the dominant Lewis structure. Okay, because it has the formal charges closest to 0. And so that's the case in this discussion. However, sometimes we're unable to pick a best structure based solely on that rule. So there's a second guideline, and it says that we look at this only if the formal charges are like equivalent, and I'll show you that in a second example here. But the second rule says that the dominant structure will have any negative formal charges residing on the more electronegative atom. Okay, and this is actually going to come into play sometimes. We're going to have to think about electronegativity. So real quick, I'll just throw this in here. Electronegativity is the desire for electrons when the atoms are bonded together, and electronegativity increases up a group and across to the right on the periodic table, with fluorine being your most electronegative. So we'll have to reference that in a minute. So So we're going to do an example with SCN minus, and this is an ion, and there's actually 3 Lewis structures that you can draw. So I would like for you to try this on your own. So pause this video. I'm just going to keep going, but you pause this video and see if you can first draw 3 different Lewis structures that all satisfy the octet rule. See if you can then assign formal charges, and then based on that, can you pick the dominant Lewis structure? Okay, so here we go. So sulfur brings me 6, carbon 4, nitrogen 5. That -1 means I'm going to add 1 here, so I have 16 total electrons. Carbon's going to be in my center with S and N on either side. And I know I have to add an electron, don't forget that. So I'm going to bond everything with a single bond. I'll put my electron here for sulfur first, which means sulfur is good and I don't want to mess with sulfur. So maybe form a double bond with those 2. And then again, knowing that sulfur is good, maybe form a triple bond with those. And I have 16 total electrons and everybody has an octet. Okay, so that's my first picture. My second picture could be the opposite of that first picture, that the triple bond exists between the sulfur and the carbon, and the single bond is between the carbon and the nitrogen. And so those are actually 2 different structures. Think about it. You know, in the left picture, I have the triple bond between the carbon and the nitrogen, and in the left or the right-handed picture, I have the triple bond between the sulfur and the carbon. So it's 2 different things, even though right away it might not look like it to you. And then don't forget, I physically have to add in that electron still. I don't know. I'll put it, I'll put it here to fix the nitrogen, or to almost fix the nitrogen, sorry. And then let's make a double bond. Oop. And then another double bond. Okay, so that's a pretty bad double bond. Let me fix that. So I now have 3 different Lewis structures, and now I'm going to attempt to pick the best one by calculating formal charge. So remember, valence minus assigned. So sulfur, 6 valence minus 7 assigned, it's a -1. Carbon, 4 valence minus 4 assigned, so 0. And nitrogen, 5 valence minus 5 assigned, so 0. In the middle picture, sulfur 6 valence minus 5 assigned, that's a +1. Carbon 4 valence minus 4 assigned is 0. And then nitrogen is 5 valence minus 7, so that's a -2. Also, I'm missing from my picture, sorry, I just realized this. These are all ions, and this is my fault here. They should have brackets with the charge. Okay. Now back to formal charges. So sulfur 6 minus 6. Oh, that's not what I wanted. Oh gosh. So 6 valence minus 6 assigned is a formal charge of 0. Carbon 4 again minus 4 assigned, and nitrogen 5 minus 1, 2, 3, 4, 5, 6. So that's a -1. Okay, so there's my 3 structures with my 3 formal charges, and so from here the discussion is, can I pick the dominant structure? So if I go back up to my rules, the first one is that the dominant structure is going to have a formal charge closest to 0. So from that information, we should be able to throw out one of these structures. And in my case, how I have drawn it, it's the middle structure because of this -2, right? The other ones have all zeros and a -1, and this one has a -2 and a 1. And so we should be able to throw out this structure first. However, this rule is not going to allow me solely to pick the dominant Lewis structure. This is when I'm going to have to go to that second rule, because they both have a -1, and it says the dominant structure will have any negative formal charge residing on the more electronegative atom. So in this case, I have the negative charge on the sulfur, and then in the right Lewis structure, I have the -1 on the nitrogen. And so thinking about electronegativity, And where do we have, let's see, we have nitrogen and we have sulfur like this. So actually this could be a, you might hesitate a little bit on who's more electronegative, but we do have got some like a chart that we could look up and confirm it. And it is nitrogen. Nitrogen's really close to fluorine. And so in this case, it's the nitrogen who's slightly more electronegative than the sulfur, meaning the dominant Lewis structure is going to be the one where nitrogen is carrying the negative charge. And so that's this one over here on the right. So that's how you can calculate formal charge. And then that's also how you can use formal charge to pick a dominant Lewis structure when there's more than one Lewis structure that technically satisfies all the rules for valence electrons and the octet rule.